welcome back. Like you haven't gone anywhere. I guess welcome me back. So I've got 2 hours of lecture left. I had a grand plan. The grand plan will be executed up to some point, but it won't be completed. So let me fill you in. Oh, this thing. You want it up here? How do I achieve that? Oh, you're going to turn the volume up? Is that better? Yeah. No? Ah, well, okay. What would you do here?
A bit more, like just add one more knot to it maybe.
Better? Okay. All right, better get on with it. So I'm the speaker, you may recall, who's actually giving this sort of broad overview and introduction to generalized linear models. Mostly, in fact, entirely, I've been talking in a completely supervised setting where we have both input representations and output representations. And in the training data that we're faced with, both are given. So I have done nothing about, unsupervised or semi-supervised training. But thankfully, another speaker has been focusing on that topic solely. I'll come back briefly to some connection there. But first, I want to complete this agenda of generalizing the representational power and algorithmic strategies that we have for generalized linear models. And as you may also recall, we've sort of finished this long survey of different sort of flexible modeling tools that we can apply on the input representation side, along with adjoining regularization strategies primarily for trying to control the complexity of the fit, or the complexity of the model class, or the fit to the data. And we've just started to move into the output side, where we're now looking at the outputs of a linear model and discovering that we can do things there like impose nonlinearities on the output to map the output predictions into a more interesting range than all of R, and yet still recover things like tractable convex training objectives and so on. Okay? The next step, which I set up last time, was to now move this enterprise into I think, ultimately the most compelling direction, which is to start to generalize the outputs beyond scalar outputs and to start to look at vector outputs, or multivariate. Okay? So step one, to go from scalar to multivariate, won't be that exciting, but we will see that we lose nothing and we gain a lot. And then once we're established with multivariate, we'll be able to take another fairly extreme step, but a very useful step to complex output structures, where in fact we're dealing with things that are implicitly, say, exponentially large or larger on the output side. Okay? At that point, I will have exhausted a lot of what's known about modeling in the generalized linear framework, but I will have also shown you at least some of the basic backbone or the basic technological thinking behind a lot of the, the current successes out there behind supervised machine learning, at least. Okay? And this should at least hopefully set you up nicely for the rest of the summer course when you have these wonderful speakers coming in who I think are going to talk about much more advanced topics. Okay, so multivariate predictions. So now we want to generalize the outputs from a scalar to a vector. Is this deep? Well, it's going to start out looking like, no, this is just obvious, right? But anyway, to get started, so we're now going to assume that our output target or output prediction is not a scalar, but say a vector. So say a k-dimensional vector. So k is right now a finite dimensional output. Okay? And how are we going to model this in a linear setting? Let's go back to linear. Well, in a pretty obvious way, the most natural way to model this is just to generalize or extend our notion of a linear model from a weight vector to a weight matrix. Okay? So we're going to represent linear models with a weight matrix in a pretty natural way, where we're going to map an n-dimensional input feature to a k-dimensional output feature by just multiplying by an n by k matrix. No big deal. Okay? If we get, I have this bad convention of row vectors here for our inputs and outputs. If we stack them all in a training matrix, we'll get some training matrix X, T by N. We multiply by the matrix W, we'll get the training responses, the output matrix on all the training data, T by K, and we'll be trying to approximate some target output matrix Y, which is also T by K in the training mechanism. Okay? Pretty straightforward. This will seem beneath you, but let's be clear. When we have a matrix like this, we're going to need to understand a bit about how we're manipulating these matrices. And there's two views of the matrix. One is we can look at the columns of the matrix, and we can look at the rows of the matrix, okay? And just so we don't confuse ourselves, if we look at a column of the matrix, what does that correspond to? That's going to correspond to one of the outputs, okay? So each output effectively in the matrix gets its own independent weight vector, its own linear model, okay? If we look at the rows in this matrix, what are they going to correspond to? They're going to correspond to features, right? So the ith row in the matrix is going to be the ith feature. Okay? This will be, useful to keep organized in our mind. All right, so we set it up that way, straightforwardly. And then what does it take to train a model like this? Well, nothing at all. We're really just right back in the same setting. The only thing we've got to do now is just impose some loss function between two vectors. Now, a loss function between two vectors is likely going to be much more interesting than just applying a scalar loss and adding it up. Okay? In fact, if we did that, it just decomposes. There's really no point in thinking of it as a vector problem. It's just a bunch of scalar problems. Okay? But if you're in something like, say, a multitask setting or a multi-class setting, as we'll see as we go on, the different output components are related to each other. They're not just independent of each other. And accordingly, the loss function, when it looks at a target vector and a guess vector, is going to make some joint assessment of how good that target assesses, or the guess assesses the target. Okay? Whatever, so we'll see some examples, but we'll pick some loss that's a loss between vectors. We'll shove it into our empirical risk minimization framework or empirical error minimization framework, and we just solve. And if we're clever enough to pick, say, a convex or at least a tractable loss function, there's nothing new here. Okay? I'm just going to alert you a bit to my notation. I don't like all these subscripts flying around everywhere. I'm just going to write it as a loss of x times w. So it's a loss between the response, the guess matrix and the target matrix. And we assume it just decomposes additively row-wise. Okay. First extension we might be thinking about is, can we do feature expansion here? Well, yes, of course, right? Like, there's no reason why we couldn't do any of what we did before, all the boosting, kernels, and so on, right? It's really just the same setting. So there's no interference with the input feature generalizations that we were looking at. In fact, I'm not going to do this in excruciating detail, but we could just replicate the whole history of what we've done already in the scalar case and discover that at each stage, really, there's nothing that deep or new, except in a few cases, okay? But generally, we can get convex training in the same sort of scenarios as before, feature expansions. We're going to investigate a bit about what it means to be doing Euclidean-like regularization and recovering kernels, and it's deeper in this setting. I'll give you a warning. We're going to explore what it's like to do feature selection through some sparsity-inducing regularizer. That also is deeper in this setting, as we'll see. We'll quickly go up to output transformations and discover this whole matching loss Bregman divergence framework that we developed is perfectly applicable here. Okay, so we can do the same sorts of nonlinear transfers and so on in this setting, or more interesting nonlinear transfers in this setting. We get our matching losses, and in fact, there's a whole analog of surrogate losses for classification and so on. Okay. So, well, let's just start going down that list quickly. First issue is, okay, what if we want to regularize? So we've done some maniacal feature expansion, okay? We're going to overfit everything, so we want to regularize. Let's start with Euclidean regularization. Sort of the way we would normally write Euclidean regularizer in this setting is just in this mysterious matrix notation trace WTW. I'll explain a bit in a minute. But essentially, this is just the regularizer that's the same as before. It's summing the squared entries of the matrix. Squaring every entry of the matrix, summing them all up. That's going to be our regularizer. It looks just like what we had before in vectors. In fact, it's just like treating the matrix like a vector. Okay? Well, anyway, let's say we impose that kind of a regularizer. Are we going to get something interesting like a representer theorem and kernels? And we're going to actually not even have to think very hard to discover, of course, right? Remember, the representer theorem had nothing to do with the loss. The only thing interesting about the multivariate setting is we've extended the loss, but it's the same regularizer, right? So without a lot of thought, we're going to discover we could rewrite the solution, some linear combination over the data. Okay? So we'll get representers, so we'll get kernels and so on as before, and we can rewrite the training problem accordingly. I want to, however, get you to think a little bit now about this regularizer as slightly more abstract as a norm. So in fact, we're imposing a constraint, just like we were before. We're imposing or penalizing magnitude of the weights, weight vectors. We really do want to think about this as imposing a penalty on the magnitude of a matrix. Okay, and we really should be starting to think about what does it mean to, how do you measure magnitudes of matrices, for example. Okay, and that's going to be very salient quickly. We're going to have to deal with that. So in fact, this sum of squared sort of typical regularizer, just to let you in on the jargon, is often called a Frobenius norm of the matrix, sum of the squared entries and so on, or it's the square of the Frobenius norm. Okay. This is silly, okay, but just, shorthand notation in matrix world is usually based on trace. Trace is one of these most useless looking operators. Why would anyone call it anything? It's just the sum of the diagonal entries of a square matrix. But actually winds up being very useful for us. For example, if I want to write the inner product between two matrices, it's just the trace of the transpose. You can verify this for yourself later. What we have already is the sum of the squared entries of a matrix. It's just the trace of the matrix squared. And we get all kinds of nice shorthand rules for differentiation and so on of traces. Okay. Okay, so there's an issue lurking in Euclidean regularization, which is how broadly are we going to be able to regularize and still get representative theorem? And I'm going to come back to that shortly. So I've left an open question. We know that Frobenius norm gives us the representative theorem. Is it the only norm that gives us the representative theorem? That's a deep question, and there's an answer, okay? But I'll stall, because I need to build up at least a little bit of recognition of some matrix norm stuff first, okay? So the easiest way to kind of get up to speed on matrix norm stuff is maybe thinking instead about regularizing to induce sparsity. Okay? And like everything, the matrix norm is going to be critical in a multivariate setting, but it's not an excuse to explore some esoteric area of mathematics. In fact, all of those esoteric things that people have discovered are just of immediate utility to us. And it turns out matrix norms are incredibly valuable and probably not even widely enough appreciated in machine learning for what they can do for us in the context of multivariate predictions. So let me just start to introduce you to this and give you a bit of a demo here. So we don't want to just penalize the squared entries, okay? We want to do something clever like feature selection. So remember now, feature selection, we're going to get a matrix, and we want to impose a penalty on the size of that matrix, but we want that penalty to do something for us. In particular, what we want it to do is select features, okay? Now, we have to be organized about this. The matrix is not symmetric, right? One way it's features, the other way it's outputs. So if we want to impose a penalty on this matrix to do something like feature selection, well, we're going to have to find a way to measure the magnitude of the weight matrix that actually really accordingly does favor zeroed out rows, right? Not zeroed out columns, for example. All right. So, well, how could you go about this? The most naive way you could go about this is say, well, let's just go on the web and start looking on the matrix norm page, okay? And you find this whole list of matrix norms, different ways of measuring the magnitudes of matrices. And it's worthwhile and it's interesting to go through and think about all the different types of norms that can be defined and all their properties. I'm just going to give you a laundry list just as a warm-up. We could look at various matrix LP norms. These are actually induced norms from a vector norm. Unfortunately, I won't be able to talk about it right now in much depth, but let's just take it as a definition. So we have like the L1 norm of a matrix, which is the maximum column sum. That's the maximum one norm of a column, okay? We have the L infinity norm, which is the maximum one norm of a row. Oh no, this is the maximum of a row. No, column, whatever. L2 norm winds up being the maximum singular value of the matrix, okay? You've seen that before. Trace norm, which many of you have seen by now because it's a growing popularity for reasons we'll see shortly, but maybe not all of you have seen it, is the sum of the singular values of a matrix. And in fact, these all define legal norms. That is, norms that are non-negative, they're zero only when the matrix is zero. They satisfy a triangle inequality and so on, okay? And in fact, norms by their definition essentially are immediately convex in their argument, right? Anyway, so we have this laundry list. There's this other class of norms that are of also a lot of utility, as we'll see, which are the block norms. Here we'll just use 2-1 block norm as an example. This looks like a useless construction, but what it does is it goes through your matrix, it computes the 2 norm, the Euclidean norm of each row, doesn't square it or anything, just the 2 norm of each row, unsquared, adds those up. So it's like the 1 norm of the 2 norms. And there's a lot of obvious generalizations of that. And then down here, our friend Frobenius. Okay, so I give you a long list of norms, and we say we want to do something like feature selection, and then the game is, well, let's pick a norm that's going to do what we need here. All right. Well, I'm not going to sort of do things in a theorem proof way. It's pretty easy to just do things in a really dumb way. But we can tell right away which of these norms is going to be useful for us and which ones are going to be useless for our purposes. Let me just do it in the most naive way possible. Imagine we have these 3 matrices, okay? And they all have like 2 1s in them, all right? And we want to do feature selection. So what is feature selection? We want to zero out a row. So we actually want a matrix U here that's zeroed out a row to be somehow favored, penalized less by the norm than, say, this one, which has done column selection. Remember, column selection in this context is catastrophic, right? You're going to zero out your predictor for some target. That's ridiculous. Let the loss function worry about that. So this is the opposite of what we want. And then here's just some general sparse matrix, okay? Well, you can check this yourself. You go through the list and you could just sort of mechanically compute the norms of these matrices under these scores. And without much deep thinking, we could discover if we want to favor sparse rows, it turns out that the block norm here, the 2-1 norm, will actually do this. Just in this example, we'll discover that it gives a smaller penalty to sparse rows than it would to sparse columns or just a general sparse matrix. Okay? So, those of you who have been seeing block norms flying around everywhere the last few years, well, it's because of this property, right? We can induce sparsity, say, row-wise. Actually, the other interesting norm, which has been flying around a lot lately, is the trace norm, which here we could see actually favors these 2 guys, U and V, equally over W. And again, this is a silly demo, but what it's actually favoring is low rank. These are rank 1, this is rank 2, and a trace norm is actually a natural way to favor low rank matrices, for example, okay? So a very shallow, kind of brief overview of the utility of matrix norms, but trust me, matrix norms are one of the most important things you need to be working with here if you want to start to be able to do implicit like feature selection or regularization learning in a multivariate setting. Okay, happily though, norms by their definition are convex, and you can just look at the 2 definitions side by side and verify that. So fine. Okay, so when it comes to what we were doing before with L1 norm, like lasso or just implicit feature selection in the multivariate setting, essentially has been based on things like block norm regularizers, 2-1 norms, P1 norms, something like that, right? Where with our same knob and our same regularization setting, but we know that this kind of framework is going to try to zero out columns or zero out rows or drop features. Okay. The related one down here is the trace norm. Trace norm is not going to zero out rows or columns, but trace norm is going to penalize rank, at least in some relaxed way. Okay? In fact, it's a convex envelope of rank in the same way that the 1 norm is a convex envelope of number of features in the vector setting. And just a sec. So if we wanted to do something like a dimensionality reduction, simultaneously with learning our input-output map, that may sound like some complicated thing where we have to bolt on a lot of extra stuff, but essentially this would allow you a cheap and dirty way to do it for free, jointly, and convexly. Okay, their hands are flying everywhere, so I'll start at the back.
Is there any guidance on when we should use the square of the norm and when we should just,
Yeah, most of the, is there guidance? That's a very good question. You probably, I think you're setting me up. You probably have an answer, but most of what I'm seeing there is algorithmic expedience, right? So you're going to find that even though this is still not smooth, that there's going to be some really nice reformulations of this optimization problem that are not available to you here, and so there are some definite algorithmic advantages to squaring them. It's the machine learning balance between computational expedience and what you're really trying to do, and I think it's just best to keep an open mind about these things. Yeah. But there are these subtle computational consequences lurking in the background. There was a question over here. Yeah?
So I'm sorry, I'm a bit lost. Because
Yeah?
So isn't it the same as subspace that?
Well, yeah, so, okay, excellent question. So I didn't explain this well. What's the difference between what's going on here and what's going on here, at least intuitively, right? Is that they're both doing dimensionality reduction, right? If I zero out a row, I've definitely dropped the rank of the matrix, right? They're both doing dimensionality reduction, but here the dimensionality reduction is basically axis parallel, right? Like we're zeroing out things, so we're finding subspaces, but those subspaces are oriented in the original feature representation, whereas here we're finding subspaces, but there's no orientation to those subspaces. Yeah, and it's just when do you use PCA? When do you want to drop features? I mean, that's a domain engineering thing, right? It's just all I'm trying to convey is that you have the opportunity to do these two things. Yeah.
Does dropping an observation ever also tell you something about whether or not it's a noisy observation or a bad observation?
Dropping an observation is a very cool thing that has a lot to do with robustness and so on, but unfortunately has nothing to do with what I'm talking about here. Yeah, I'm dropping features. I'm not dropping any observations. You would want to drop, look, dropping observations is related to robustness, right? Like, dropping an observation would be a very useful thing to do if you want to get rid of an outlier. Yeah? And, oh gee, I had a grand plan for talking about robust, but I'm thinking I may not get there. We'll see. Okay. All right, so, sorry, that's enough of this. You get it. Okay, let me just finish. Oh, yeah? How does the max norm connect to this? Or are you talking about, like if we go way back here, like this guy? I don't know, it seems pretty useless. Do you I don't know, maybe some use will be found for max norm in this context. Not everything has to have an immediate use, does it? I don't know, I can't think of a, I mean, there are like 1 infinity, block norms using the max norm definitely are in use. Yeah. I don't know, but I wasn't using the max norm even in the vector case, by the way, actually for good reason, but I didn't talk about it. Yeah. Okay, sorry. Last thing I want to say about sort of matrix norms. Again, this is my just survey, trying to make sure I touch all the bases for everyone. But there is this very interesting question, which is, once we kind of look at matrices and we think of like general norms on matrices as general ways to penalize magnitude, we started with Frobenius and we discover we get representative theorem and we're happy. But what happens if we pick something fancier, like say 2-1 block norm? Do we get a representative theorem? Do we get kernels? If we pick trace norm, do we get a representative theorem? Do we get kernels? And up until very recently, this was done on an ad hoc basis. Somebody would think really hard about this one norm and figure out that yes or no, you do or do not get a representative theorem. Okay. Happily, finally, this has been nicely settled, right? And just in the examples I've shown you so far, it turns out the 2-1 block norm, just like the L1 norm before, blocks the representative theorem. It does not allow the same equivalent adjoint formulation. But amazingly and usefully, the trace norm does. And in fact, there's a whole family of norms that wind up satisfying these conditions I haven't talked about yet, that give you a representative theorem. And the family of norms here, the Schatten norms, are the ones that basically are just norms on the singular value vector of a matrix. So you do SVD, you get all singular values, they're all non-negative, and you look at a P norm of that. If you measure, and winds up, those define matrix norms. And if you use those matrix norms, you wind up still recovering a representative theorem and still getting kernels. So quickly, as a consequence, we'll see the trace norm and variance of trace norm, or spectral norm, which would be also another Schatten norm, would allow a representative theorem. The general condition is actually quite simple and quite pretty. If I put a regularization function, some function R, on the matrix here, what are the functions R that allow a representative theorem? And it's any non-decreasing function, we had that before, of the matrix inner product, right? And there's just a nice, elegant proof out there right now. So this is really, pretty recent and a very nice settling of the question here. So essentially in the multivariate case, we have about an equivalent level of understanding that we did in the vector case, even with the much richer structures that we're playing with. So that's good news. It's kind of neat. Okay. Oh, yeah?
What do you mean by non-decreasing function of W transport? What is W?
Oh, yeah, it was a special matrix non-decreasing. Yeah, so, okay, so matrix non-decreasing function of this inner product, okay. Well, first of all, we know that the argument here, so, did I write this? So think of a function of that product. So we have a function t, okay. The argument for t is semi-definite, right? It's guaranteed to be a positive semi-definite matrix. So, so all we need is a non-decreasing function defined on the set of positive semi-definite matrices. Okay, and the natural way to think about positive semi-definite matrices is there's an ordering on them. It's a generalized ordering based on based on this semi-definite ordering, which is this. Oh, I didn't show you this definition. Ooh, well, anyway, yeah, you can learn. Anyway, this just means A minus B is positive semi-definite, and this gives you an ordering on semi-definite matrices, and we mean non-decreasing with respect to that ordering. Wow, I really kind of just hit a lot under there. Non-decreasing functions. I mean, it's not that complicated. It just takes a little bit of time to go through it. Okay, I got to keep moving along. So, okay, next step. So we've gone from scalar to vector. We know how to represent linear models that map vectors to vectors. We even know how to regularize linear models that map vector to vectors. And we can deploy all of our regularization thinking in terms of feature selection or just getting kernels, maybe even trying to do two of them together. But likely that's going to wind up being about as ugly as it was in the vector case. Okay. Next step, I have to make sure I can go back and generalize the outputs. So right now, we're still talking about an output predictor that's a linear map from the inputs, and we definitely need to impose nonlinearities on the outputs in the vector setting. You won't be shocked to see that we can do that. And the way we do it is just like I already introduced to you in the scalar setting. We're going to introduce nonlinear transfer functions and define a matching loss construction around those that are going to lead to Bregman divergences. Just one thing I should point out to you. Okay, so this is what we'd like to do. I want to impose some nonlinear transfer now between my linear pre-prediction to my nonlinear post-prediction, right? And then I'm going to make my post-prediction is what I'm going to compare to my target. So for example, we're trying to predict vector targets. What if the elements of the vectors are non-negative? There's a pretty natural idea. We could still use an exponential transform, okay? What if the output that we're trying to predict is a probability vector? That is, all the entries of the vector are between 0 and 1, but in fact, they sum up to 1. So it's a joint definition, okay? Is there a way that we can take an arbitrary vector and map it into probability vectors in a nice, smooth way that we can still get a matching loss for? And the answer is yes. It's an obvious transformation. I'll show it to you right away. Okay. The other kind of transformation we would be interested in would be a multi-class classification transformation. So what if we had a K-class classification problem? Well, the natural way to think of it is, well, there's many ways we could represent it as a bunch of binary problems, but one way we could represent it as just a joint vector problem is just to have a K-length vector that's an indicator. It's a vector that's all 0 with a single 1 indicating the class. And then what if I give an arbitrary vector the same length as my pre-prediction and I want to map it into a post-prediction? Well, then we would have a transfer that would basically find the arg max and then map that to a 1, everything else to a 0. Stuff like that, okay? Oh, and it's right here. So here, for non-negativity, we could just exponentiate component-wise, right? If we want to map into probability vectors, there's more than one way to do this, but a natural way is the softmax, right? This was, again, popular way back in the neural net days, but you exponentiate everything and then you renormalize, just divide out by the sum of the exponentials, and you're just going to map into a probability vector. And it's a nice, smooth, differentiable, happy function, okay? And then here's our ind max. Now, I confess, I could not find a name for this transfer. I just made this up. You won't, I don't know. Ind max, right? So it takes a vector, it finds the location of the max, and then creates an indicator vector that puts a 1 there. maybe there's a name, I'm embarrassed, but in-max, okay? So these would be sort of analogous transfers that we saw before, but now applied to the vector case. Okay, question though is like, okay, sure, we can always impose nonlinear transfers, but are we going to be able to engineer some, say, it would be nice, perhaps, for some of us, if we could engineer a convex loss, or a loss to apply in that setting that would still allow us some convex globally trainable setting. And we'll see that it's easy to do that here. Well, but it's not quite as easy, because in the scalar case, I showed you this matching loss construction. In the scalar case, we could just pick the transform, f, and f just had to satisfy very simple properties, like, you know, differentiable, strictly increasing, some other property. Okay? But here, it's not going to really go that way, because it turns out that the f has to satisfy another property that's really implicit and hard to work with. It's going to turn out that the transfer f, little f, is going to have to be the gradient map of some potential function, which is just a mouthful of jargon. But let me just start again. Forget about the transfer. We do want to transfer, but the way you engineer the transfer, at least most easily, is you start out with the potential function, right? The function whose gradient is the transfer. So in the multivariate setting, we mostly engineer these things by picking different potentials. So a potential function is a function that maps a vector to a scalar, right? It's a scalar output, right? The transformation maps a vector to a vector, okay? So we pick a, you know, just a regular real-valued function that is strictly convex. Any one you like. Any function, real-valued function that's strictly convex, if we look at the gradient map, you know, the gradient, right? That's another function that maps a vector to a vector of the same length. That's what gradients do, right? And that gradient map is going to be the nonlinear transfer, okay? I have the examples where the things we did before are exactly this, just gradient maps for a potential. But if we want to, so I'll come back to that in a moment, but say we pick a potential we're happy with because it has a gradient map that does what we want it to do, it maps into the range that we care about. How do we construct the loss? Well, then we're just going to construct the loss using the same Bregman divergence construction. We're going to essentially just use a Bregman divergence. We're going to say the new loss is just the potential of your pre-prediction guess minus the potential of the pre-target, you know, minus the gradient map on the pre-target, inner product with the pre-guess minus pre-target stuff, okay? Just that's the definition, and this is going to lead to a problem that's convex in z hat. Okay? This looks hacky, but again, we'll discover if we plug in natural choices, magically recover standard losses that people use. We know actually all these nice properties from before are going to hold because of the same sort of Taylor. So if f is strictly convex, then we know this is a difference of a function in the Taylor approximation. Therefore, we have the inequalities, and we know non-negativity follows. We know we get zero loss only at the exact guess point, and so on. Okay? So it's a well-constructed loss. Maybe just to make it more concrete, we could look at some examples. So we could do exponential transformation by starting out by picking a potential. And we'll pick a potential which is, say, just the sum of the component-wise exponents, exponentials. And then we take the gradient map, and we discover that's just the exponentiation component-wise. And we say, ooh, see, that was our transfer from the potential. And we get. And then we go through the matching loss construction. We discover that we reinvent the corresponding matching loss, which is the unnormalized entropy. That's what falls out, and again, this is derived by independent means in various areas of information theory. For example, you know, it's a well-known loss. Okay, perhaps more useful in most machine learning contexts is the softmax. So here we have this rather unmotivated-looking potential, but it's the log of the sum of the exponents. Those of you who've looked at convex analysis a little bit so far know log sum exp is one of the famous convex functions. You know, you look in Boyd and Vandenberg and you check it out, it's in their list, right? So this is the log sum exp. It's strictly convex, nice approximation of max. And if we look at the gradient map, we get this softmax transfer that, you know, 25 years ago people were just inventing by hand in sort of old neural net days. Right? Fine, so we get the potential, we get the transfer, we plug it into the Bregman divergence construction, and out pops a loss, and the loss that is matched to these things is KL divergence. Kind of cool, okay? So the loss function is the KL divergence between the target distribution and your guess, the target probability vector and your guess probability vector. And so this is obviously a very common potential transfer loss framework to use in a multivariate setting where you're doing something like probabilistic classification. Okay? And this will generalize wonderfully into a structured output setting where, in fact, things are implicitly exponentially large. We'll see later. Oh, classification. So there's the, of course, the ind max, this step threshold-like transfer is highly problematic, right? So none of these matching loss constructions apply. We're stuck with hard combinatorial problems. You know, it's pretty bad, but people persist. And so in the scalar case, the persisting looked like this idea of a fake loss or surrogate loss. And there's a direct analogs to exactly those constructions in the multivariate setting, okay? Won't spend too much time, but you know, we have this analog of a margin loss for multivariate predictions. And that would just be some loss function that depends only on the inner product. Let me explain this a bit. So our guess is a 0, 1 vector with a single 1. And our targets are 0, 1 vectors with a single 1, say on some target class. So the margin, well, it doesn't quite work out the same way, but we use both the, this inner product and that. What this inner product is winds up being just the response on the correct label, right? Since y is an indicator and I have some pre-prediction, this is my pre-prediction response on the correct label. And then this is my entire vector of pre-prediction responses. And then margin losses will be defined in terms of these two quantities. What's your correct response versus the rest of the responses? And there's various ways, you know, that we could tune those up. Of course, the only thing we care about is that the correct response is bigger than the rest, right? Because that's the classifier, right? The classifier is just classify according to the max response. And if that max response is correct, you know, 0, 1 misclassification error is 0. But you know, we can't train like that very tractably, so we're going to introduce surrogates based on these two quantities. For example, actually, let me start down here. The multi-class support vector machine loss, which you know, was a clever construction. You know, Yoram Singer and Kobe Kramer. But you know, back then, you know, people had to think about this stuff. Of course, now there's many variants, but this is a pretty natural variant. This is like a large margin loss, which I guess you have to decode this. But what this is trying to do, you can see with a little bit of thinking, is it's trying to push the response on the correct label above the response on all the incorrect labels plus a margin. And it's, you know, it's a ramp-like, you know, piecewise linear function, okay? Well, we see it's piecewise linear because it's linear and it's a max of linear. Max of linear is piecewise linear, and it's convex. Multinomial deviance would be the analog of the binomial deviance, which is a log sum x minus that there. And this actually looks a lot like a log likelihood, and it is, or negative log likelihood. But it's a smooth version, right? Okay, anyway, just some examples of what people do for surrogates. And remember, surrogate training is we put in the fake loss, we train on the fake loss, and then in test, we forget about the fake loss and we use the real loss. Okay. Maybe I shouldn't dwell on this. Multi-class SVM. So you can, I just like to show that you can write a multi-class SVM in a matrix vector notation very compactly. And in fact, if you want to derive a dual quadratic program to this quadratic program, you could maybe pose to solve a multivariate SVM. You know, you could do it by subscripting things in I and J, and you can spend 5 pages deriving it, or you can do it in a couple of lines in matrix notation, but I'll spare you those details. Why do we get, you know, with support vector machines, again, why are we getting things like kernels and so on? Well, actually, it had nothing to do with this hinge loss at all, right? It was the fact that we're always just implicitly subbing in Frobenius norm, just the Euclidean regularizer, right? There's nothing to stop you. Hopefully people don't start writing papers like this, but there's nothing to stop you from putting in a trace norm regularizer and starting to do dimensionality reduction while you're training your SVM. There's nothing to stop you from doing block norm. Oh yeah, that's what people are doing in multitask learning. Anyway, you know, we could generalize our regularizer with the norm. The loss and the regularizer are just independent things. And a lot of the, you know, the properties we care about, feature selection properties, dimensionality reduction properties, kernelization properties, have nothing to do with the loss, right? They're just about how you regularize. So, you know, we can, you know, even with like piecewise linear losses, we could have all of those other mechanisms in play if we so chose. And I don't know if the research literature has filled out the full table of all combinations, but you don't need me to tell you that the research literature's job is not to provide you with a simple, coherent view of the field, right? It's to fill in little corners. And so I think there's a real risk that a lot of these very obvious things aren't really sort of widely appreciated, and then people discover them midway through their career and they just get really frustrated, okay? But a lot of these are pretty easy things to figure out. Yep?
Maybe we're going to get this later, but with the regularizer, if we go Bayesian, there's kind of a probabilistic view of what that means.
Yes.
You're going to talk about it later.
Yeah, if I keep talking fast. Yeah. Yeah. Okay. I think structure. So, boy, I thought, I got new glasses. I thought I could really see, but it looks like I got about 10 minutes. So I'm going to do one more topic in 10 minutes, and then we'll take a break. Of course, it's the worst possible topic to do in 10 minutes because there's details. But I think I can do this. No, that sounds like a good idea, but there are consequences to that idea. So now I think I can do something reasonable in 10 minutes here. Okay, so this would be, think of this as the last extension on the output side. So remember, I start with simple linear models, and then I spend a day trying to extend the inputs, and then another day trying to extend the outputs. And sort of the pinnacle of what we're doing on the output side is going to be this last step, which is, we could try to think of it in many ways. One way to think of it is, instead of outputs that are just vectors, multi-class problems or just, multivariate predictions, what if the outputs were actually interesting? What if it was like a parse tree? What if it was like a sequence label? What if it was like, a partition of a scene, right? We would like to be able to map, from our fancy input representations through some, interposed linearity to a structured output, okay? Now, look, I'm not going to solve image parsing for you, right? But I want to just show you some of the steps that people understand very well in how we impose structure on the output so that we can handle implicitly large output structures and still do it tractably within this framework. And it's going to tie in nicely to graphical model structures and message passing algorithms and so on, as you would probably guess already. But the interesting thing is we lose nothing. It's completely orthogonal to all the input, all the regularization, all the dimensionality reduction, all of it. It's completely orthogonal. It could be applied, okay? Okay, so structured output prediction. So the game here is, I ran out of energy for making slides, but imagine you have something like an OCR problem, right? So you're scanning images of handwritten digits and you're just trying to map them into, some machine readable text, right? And here, what if, so I'm not showing the images, but what if I have some, if you saw my handwriting, you'd say like, in fact, this is a natural interpretation of my handwriting version of the red apple. Okay, but there's all kinds of things. Like if you look at my writing, the Q's and the A's look the same, the E's and the C's look the same, the N's and the R's look the same, the F's and the P's look the same in my writing, right? And so if you do OCR, we could treat each, say each segmented, say we even segment, each segmented image as a separate classification problem. I look at the image, I got to map it into a character, okay? But of course, that's not the way language works, right? Even if you had a high fidelity character predictor, it's going to be quite poor in practice because the truth is, if you look at an F I write in one context and an F I write in another context, they look more like P's than F's, objectively, right? What we use mostly in our perception, for example, is we use a lot of context. Like the person who wrote this is actually trying to say something, right? And so it's pretty easy to disambiguate. Even if I gave you these lines, you'd probably figure out what I'm trying to say is the red apple, right? What are you doing there? Well, you're not using, there's no OCR here at all, right? You're not using anything on the input side. What you're using is context that's entirely about the output, right? I'm just using output context. RCD is not a word. RED is a word. E looks a lot like C. It's probably red, okay? So this is, obviously a toy demo, but this kind of structure on the output space is something that we want to be able to capture, and people, have worked out quite well over the last 10 years, at least reasonable ways to start to capture stuff like this, and it really matters. It really helps in practice. Those of you who are doing, for example, NLP, this is just what you do all day. Okay, so there are strong mutual constraints on the outputs. So we want to treat the whole output jointly. We can't factor it into independent prediction problems. We have to have a joint prediction problem. But the difficulty with a joint prediction problem is that the joint output space is vast, okay? And we're going to have to exploit a lot of structure, techniques to be able to represent things compactly and then do all of the computations efficiently. Okay? So if we focus, say, on a classification-like setting, we would have exponentially large output sets, and we can't represent or even enumerate. We have to do something smarter. I'll just give you a quick preview of what people do, but I guess a lot of you would know this already. What we're going to do is think of a single input-output pair. We're going to create some big feature representation, but the feature representation, actually, I could have written this as a matrix, but it's just easier to write it this way. The feature representation is going to be features of the inputs and the outputs. Okay? So we're going to featureize not just the inputs, we're going to featureize the outputs also. This is a very useful trick, okay? But we're going to stick to a linear model on top of the features, but now it's linear on input features and output features. In fact, there's just kind of joint input-output features if you wanted, okay? Now, we're going to need to impose structure. So I could have a very compact representation of an input-output pair, but it turns out that computationally we're going to need to exploit other kinds of structure just to be able to do things that we're going to need to do shortly. So a common form of structure is that we're going to take the output and we're going to break the output into local neighborhoods. So let me just use sequences as a simple toy demo. I'm going to take a sequence of output symbols, and then I'm going to make a graphical model which connects pairs. I'm going to have like little cliques that are on pairs. Okay? And so I'm going to break my big input-output representation into a decomposed sum of local input-output representations, where the local, I should have indexed this by L too. Anyway, our local input-output representation, which depends on a clique. Now, it doesn't have to just be two elements to the clique, but in a sequence we just have cliques of pairs. Okay? So I have local features, local input-output features, and my overall feature representation of a big structure just decomposes additively into the sum of all my little local feature representations, or my little scores. Okay? Not anything will do. It turns out if I set it up so that the structures form a graphical model, and the graphical model has nice properties like junction tree with small tree width, or put it another way, say it's a tree or a sequence, we're going to have efficient algorithms just like we would pull out of standard graphical models. Okay? All right, so that's sort of the game, how we tie this kind of generalized output structure into a graphical model, or even more generalized parse tree or graph matching representations.
Could you maybe frame that in terms of the previous slide's problem, so I can understand what you mean by local?
So just think of sequence label. So let's do sequence classification, right? And in fact, make it some binary sequences. So I get stuff, and I have to produce a corresponding output label, and the output label is just a binary sequence. But there's the pairs, like maybe the 1-1 transition is preferred over a 1-0 transition or something. One way I can just represent it entirely in the previous multivariate setting is kind of like a decomposition. So I take my data, and I'm just going to stack it in a matrix. Okay? But on the output side, what I'm going to do is, say I have like k classes or 2 classes. Instead of output vectors that are of length 2, say for the 2 classes, I'm going to make output vectors at every location that are of length 4, a pair. So what I'm going to do is I'm going to encode pairwise joint labels, so clique labels. Okay? So every location, I'm going to break my data up into independent pieces. Every piece is predicting a pair. Okay? But on the output pairs, between 2 vectors that are indicating 2 different outputs, there's a constraint because they're consecutive, which means a label here and a label here, they have a joint common label, and that constrains. So we could write everything in the same matrix vector notation that we had for the multivariate by just doing a clique expansion over the label and then imposing constraints on what legal paths essentially look like. A legal, say it's indmax, right? So we have a legal bit indicator and their legal paths. I don't know if this is helping, but this actually I was going to try to teach it this way, but then.
Is it like predicting bigrams essentially for the?
Yeah. Let me go. Let me go a little further and then see if we can sort this out. Okay, maybe I'll start in the middle here. So let's, okay, there's a training problem. Remember, the only thing we're doing in a training problem is we're learning our linear parameter, so W. So, okay, some magical black box, we download the code in the web, and then we hit solve, and it gives us a W, okay, over our data. Step 1, do we even know how to use that W? Well, what we need to be able to do is just classification. So I get some new test document or sentence or image, and then I want to produce the structured output. How do I do that? I have to solve this computational problem. I have to search over all possible labelings, joint labelings over the whole sequence, to find the one joint labeling that gives me, say, the maximum score with the linear model. Okay? Now, this is an exponential search. Right? So we need to exploit that structured, say, graphical model structure as an example, as a way to efficiently be able to compute this. Okay? Now, we'll find in other parts of training, okay, so this would be like a max sum. We're going to discover, oh, here it is. So if I take this joint thing and I break it up, it's a max over sum of the local context of local scores. So we're going to need to be able to take a structure and solve a max sum problem. And that will be our structured classifier. During training, we may need to be able to do things like solve a sum product form. Okay? Again, those of you who know graphical models, this is just known. Those of you who don't, this is probably not good teaching of it. But anyway, that's what's going on there. And so we're going to exploit a combination of the structure, local structure, and sort of tree-like constraints, and distribution properties between sums and products, or between maxes and sums, to decompose these computations into tractable computations. If we can decompose these computations into tractable ones, then we can do both training and prediction tractably. Okay? I'm afraid to put up the next slide, but I just did. So I'm just going to do this as a demo. Okay, so here's my exponential search. So what happens if I have a bunch of pairwise score functions over the 4, 5, 3, 4, 2, 3, 1, 2. Okay, and I want to find a maximum joint assignment over these variables of a sum, but the sum is a sum of local components where there's a sequential clique structure. Okay, this is an exponential search, but it turns out just by the simple distribution properties between sum and max, or product and sum, right, we can quickly get linear time algorithms, right? Just by distributing the maxes through and then collecting up the guy in the bottom. That's a fast computation. Once I have this solution, I can solve this quickly and then back it up. And then once I've got this solved, I can solve this quickly and so on, right? And so you reduce order alphabet size to the k down to k times alphabet size squared. Right? So, computer scientists should like this, right? Exponential time to linear time. That's good computer science. Come on. So, we can exploit certain structural properties to dramatically reduce computational costs.
That was because due to the locality structure?
Absolutely. So not just locality, but locality and structure. So it's a graph, right? Think of it as a graph. Like each pair is a node, and then connect the nodes, and we wind up with a chain. A chain is a tree. If you have a tree, you're going to be able to get this factorization for free. If it's not a tree and it's a loopy graph, you got to do more work. If you want exact computations, like build a junction tree, which is a clique tree with a special property. I'm sorry. Yeah. Anyway, do a web search for like graphical models. Anyway. Yeah, and I'll wrap up quickly. And so we would get the exact same, this is a silly slide. It's the same as the previous slide, except instead of maxes and sums, we have sums and products. But you can see the algorithmic structure is identical, okay? Even though historically the algorithms that first got invented had different names. Like one's called Viterbi, the other one's called forward-backward, but they're the same algorithm. And we've known for a long time now that it's just the same algebraic structure that's being exploited. Okay, and I'm gonna stop there and think about how I can get myself out of here. So a half-hour break, and then I will finish my sequence. Okay, thanks. Oh, thanks.